look for the remote. Yeah, so nice for you to be here. As Bas said, my presentation will be on the paper I've written about my master thesis. It's called The Effect of Chordwise Deformation on Steady Aerodynamic Mechanisms in Hovering Flapping Flight. Wrong remote. So, yeah, just let me. Oh, okay. So, well, okay.
I'm sorry.
Yeah, can the lights go back out? Yeah, thanks. Okay, so this will be the overview of my presentation. First, I will clarify what I mean with unsteady aerodynamic mechanisms, because I'm not sure everyone's familiar with the term. Then I will tell about the goal of this study. I will show you the setup of my numerical simulations, and then some results and conclusions. So, unsteady aerodynamic mechanisms, like Bas already mentioned, the aerodynamics of flapping wings are quite different from those used in fixed wing aircraft or rotorcraft. For that matter, instead, they rely on unsteady aerodynamic mechanisms for the generations of their lift. Now, there are three important mechanisms I like to point out and quickly discuss. Those are the stable leading edge vortex, wake interaction, and clap and fling. Now, there are several others, however, I'm not going to go into detail about those. So first, let me quickly discuss stable leading edge vortex. What happens when a wing at high angle of attack starts to translate? You can see in the top left, when it starts to move to the right, flow will separate near the leading edge, and it will retach somewhere along the wing, creating a leading edge vortex. Now, when this happens in an ordinary wing, this vortex will grow, temporarily creating a large low pressure region on top of the wing, creating high lift. However, if the wing continues to move, this vortex will shed, resulting in a loss of lift or stall of the wing. However, what we see in, for example, flapping insect wings is that this same vortex is created and it remains attached to the wing, creating very high lift on the flapping wing. So this is a very important lift generating mechanisms in flapping wings. Second, wake interaction. Well, inherent to flapping flight is that, especially when you're in hover, the wing constantly moves through the wake left by the previous stroke. Now, this can have both positive and negative effects on the generation of lift. And we have to see which one applies for this case. A quick example of how this would generate a positive effect on the lift. So here you can see again in the top left the wing moving to the right. With the leading edge vortex, then as the wing starts to prepare for the following stroke, it starts to rotate. Both the leading edge vortex and the trailing edge vortex shed. Since these are counter-rotating vortexes, the air in between them is accelerated, creating an extra flow and speed-up flow towards the wing, and this creates temporarily an increase in lift. And finally, there's clap and fling. These are actually two separate mechanisms. They just usually occur together, so they're mentioned in the same phrase. Clap is the first thing that occurs when the wings come together. You can see first the leading edges of the wing will come together, then the air, then when the rest of the wings come together, the air in between the wings is pushed down, pushed out. This creates a small upward jet, of a downward jet, and a small upward force. Afterwards, fling is when the wings come apart again. Now you see the leading edges go apart first. This creates a low pressure region in between the wings. This almost instantaneously creates leading edge vortexes, and like I said, these leading edge vortexes are very important for the generation of lift. So in this effect, it will increase the creation of lift. So the goal of this research is to investigate the effect of the chord deformation on this aerodynamic effect. And I want to do this to improve the understanding of the physics involved in flapping flight. So I'm not here to say this type of deformation is best for your wing or anything. I just want to improve the understanding, and designing better wings is up to you guys. Yeah, like Bas also mentioned, I'm going to use this doing a numerical simulation. This is because we can, in this way, we can get a nice 3D, three-dimensional overview of the entire flow field. And I will use a prescribed deformation for the wings. So let me show you the setup. First of all, I modeled a single wing as a flat plate with an aspect ratio of 2 and use a symmetry plane to mimic the second wing. The Reynolds number, based on the average tip velocity, is around 2000, and we have a flapping angle of 45 degrees. Now, if we don't do anything, this will look something like this, with the lift defined in negative z direction, that's up. As you can all see, this would not generate any lift, so I add deformation to this plate. First, I define 3 types of deformation. First is actually rigid pitching, that's just pitching around the leading edge. Then there's a case with the maximum deformation near the trailing edge, and a case with the maximum deformation near the center. So when I use maximum, so this is rigid pitching, but no pitching near the root of the wing, and maximum pitching near the tip of the wing, and a maximum angle of 30 degrees, and this will look like this. Then the deforming end case, I call this. It's a maximum deformation at the end. It's quadratic deformation. And as you can see, this will increase the effective angle of attack near the leading edge, which will be important in the creation of a leading edge vortex. This will look like this. And finally, a case with the maximum deformation near the center. Again, quadratic. However, now you can see that the angle of attack near the leading edge is decreased compared to the rigid case, and this will look something like this. Good, so results. These are lift coefficients of one entire cycle, so that it starts with an outstroke and then an instroke. There's 2 peaks in lift. And the straight lines, those are the average lift coefficients. You can actually see from this that both the deforming cases create a slightly higher lift coefficient than the rigid case. However, I'm not particularly interested in the actual lift coefficient that's created. I'm interested in the unsteady aerodynamic effects. Now, the first of which was the leading edge vortex. So let's first look at that. This can be clearly distinct from the start of the outstroke. Here you can see the green line, that's the deforming end case, and it has the fastest buildup in lift, and the deforming center case has the slowest buildup in lift. Now this has to do with the decreased angle of attack or the increased angle of attack near the leading edge. So on the bottom I have plotted Q criterion, which is a good indicator of the vortex. In the middle, you see the deforming end case. You see a much stronger leading edge vortex near the leading edge compared to the other 2 cases. And in fact, this higher angle of attack instantaneously creates, or not instantaneously, but starts creating a strong leading edge vortex almost right away, resulting in a much stronger buildup of the lift coefficient. This in the next time step, you can see the leading edge vortex of the deforming end case grows much faster compared to the other 2 cases. Now, another interesting thing to note is there are clear humps in the lift buildup. You can especially see that in the second peak during the in-stroke. You see clearly lift buildup and then a hump in it. Now, like I said, leading edge vortex stability is very important and one of the main generators of lift in flapping wings. So if we see such a hump, it's quite natural to assume that this leading edge vortex has shed. So let's see if this indeed happens. Well, these humps are clearest during the second peak, during the in-stroke. So let's look at that first for the deforming end case. Here I've plotted again Q criterion on these 3 crosses you can see during the lift buildup. Now, it's hard to point, but the leading edge vortex is actually, so the wing is moving to the right. So the leading edge vortex is behind the wing. And you can see it moves down a little bit along the wing. However, if you compare, for example, the middle one and the one on the right, then the lift starts to build again. And it's hard to explain it using just this leading edge vortex, because there doesn't seem to be some shedding going on between the first and second picture that isn't going on between the second and the third picture. So it's hard to actually get this from shedding of the leading edge vortex. And the same is true when we look at the rigid case. We see, again, a build-up now for the first 2 points, and then at the third one, you actually see a certain decrease in lift. But we can't really explain this, again, from shedding of the leading edge vortex. So, again, something else has to be responsible for this. So some of you may already have wondered, I know it's early, but some of you may have already wondered what this large vortex in front of the wing is. Well, that's actually the vortex shed from the previous stroke. And looking at the three-dimensional view of the flow field, we can clearly see what I'm talking about. This, so on the top is the start of the in-stroke. The wing will now move towards us. So this large, these are isosurfaces of the pressure, negative pressure. Like I said, vortex create low pressure regions. So plotting isosurface of negative pressure will show you these vortex structures. Now what you see in front of the wing is the vortex shed from the previous stroke. And in the deforming end case, you can see already at the top of the wing the new leading edge vortex starting to build. Then one time step later, we can actually see that the new leading edge vortex in the deforming end case starts to interact with the vortex from the previous stroke. So we get this interaction. And in fact, this moment in time corresponds to this hump in the lift buildup. Then if we continue, we can see that in the next step, this interaction is finished for the deforming end case. And in fact, we see the lift rise again. Now for the rigid case, we now see this interaction. And again, this corresponds to a hump in lift coefficient. And afterwards, when we see the lift rise again, indeed, this interaction is finished. So we can see that a hump in the lift coefficient is in fact caused by interaction between the leading edge vortex and the vortex shed from the previous stroke. Now for the case where the deforming center case, which lowers the angle of attack near the leading edge, we don't see this interaction, and here you can clearly see why. Because the deformation that increases the angle of attack near leading edge, you can see, first of all, it's the leading edge vortex builds much faster, but also it pushes the vortex shed from the previous wake up towards the leading edge vortex. And then you can see in the deforming center case, actually the previous shed vortex is pushed below the wing, and the wing in fact shields the two vortices from each other, preventing this interaction, which is clearly beneficial because it prevents this hump in the lift buildup. Now, and just to be sure that indeed interaction between the previous shed wake and the new wake, and the new vortex is responsible for this hump, we check the initial stroke, because of course if you have the first stroke, then there's no previously shed vortex, so there shouldn't be any hump. And indeed, looking at the lift during an initial stroke, we don't see any humps. So indeed we can say this hump in the lift buildup is caused by the interaction between the new leading edge vortex and the previously shed vortex. Then the last aerodynamic mechanism I wanted to talk about is the clap and fling. I investigated this by first simulating a single wing and then moving a wing close to a symmetry plane. Now you don't have to completely make the wings touch to get the effect of clap and fling. You can in fact get that by moving it closer, and we can see this quite clear. Now I did this for the rigid case and the deforming center case, and from this picture you can see, although the distance from the leading edge to the symmetry plane is equal for both cases, due to the deformation in this deforming center case, you see that a larger part of the wing is near the symmetry plane. So we would expect the effect of clap and fling to be more pronounced for this deforming center case. So let's see if this is indeed the case. So this is for both the rigid wing and the deforming center case, the increase in average lift coefficient compared to a single wing. Now we see that when we move the wing to a distance of 0.5 chord length to the symmetry plane, in fact, for the rigid case, the average lift coefficient increases with 3.4%, whereas for the deforming center case, it increases 5.1%. So indeed, this increase is larger for the deforming center case, as we expect. However, when we move it even closer, you can see that the increase for the rigid case is actually 11.3%, and for the deforming center, only 9.2%. So now, instead of being larger for the deforming center case, it's larger for the rigid case, which is not what we would initially expect. Now, to see why this is the case, we can look at the lift coefficient. And what we can see here is that indeed a much stronger lift buildup due to the Fling effect, the almost instantaneous buildup of the leading edge vortex. You can see faster lift buildup. However, this also causes this hump, this interaction between the new vortex and the previously set vortex to occur faster. Now you can see for the rigid case, this isn't as big a difference because this interaction was already quite strong and it just moves ahead. However, you can see for the deforming center case, this interaction happens way earlier, but it also takes a lot longer. And this is due to the shielding of the wing between the two vortices. It limits the interaction, but only after the interaction is complete can the lift start to build again. So in this case, the fact that the interaction is made so difficult actually hinders the lift buildup. So the effect of clap and fling is reduced. Now then, conclusions. When we have a deformation cause a higher angle of attack near the leading edge, this results in faster leading edge vortex buildup, and with this faster buildup of the lift coefficient. We didn't see any shedding of the leading edge vortex, which is very important. So in fact, increasing the angle of attack creates a strong leading edge vortex, but no shedding, so that's only beneficial for this case. However, what we did see is that interaction between the new leading edge vortex and the previous set vortex had a negative effect on the lift coefficient, and that we also saw that when the deformation causes a lower angle of attack near the leading edge, that this interaction takes longer, and so it is in fact beneficial to have a lower angle of attack because it limits this interaction. Now, as for clap and fling, we saw a clear beneficial effect on the lift coefficient and the lift buildup, and this was initially more pronounced in case deformation caused a larger part of the wing to be near the symmetry plane. However, we also saw that when they became too close, the interaction between the new leading edge vortex and the previously set vortex actually occurred much faster, and this limited the benefit of the clap and fling. That was my presentation. I hope you enjoyed it, and if you have any questions, feel free to ask.
Okay, the paper is open for questions. And if you have a question, Tijs, please repeat the question so that.
Yeah.
So, based on these conclusions, what could you say for the design? Let's say, how could you, of course, very practical question, how could you perhaps make it bend the way you think is most beneficial?
Okay, so the question is, how would you maybe implement these results into an existing design, or how would you make a design that benefits from these results? Well, to be honest, that's first of all, it's very difficult to say because these deformations usually flapping wings, they use a very flexible design, so to make them deform in such a way is non-trivial. Of course, you have to remember these are prescribed deformations. However, you can imagine, for example, if you want to simulate clap and fling, it will create a large low pressure region in between the wings. So if you have completely flexible wings, the shape will be influenced largely by this low pressure region. So to have pre-designed shape is rather difficult.
And the sensitivity, like to the parameters, so you took some parametric shape for example, the bending.
Yes.
How sensitive do you think your results are to the exact parameters? Suppose you make it slightly hollower or slightly, do you think it will have a large influence on the results?
Okay, so again, the question is how would the how sensitive are the shapes to these results?
The results to the shape.
Yeah, sorry, the results to the shapes. Yes. Well, the thing is, the things I tested are, for example, very important is the increase in angle of attack near the leading edge, and of course, if you have a higher angle of attack near the leading edge, it will speed up the creation of a leading edge vortex, speeding up the creation of lift. So this is, well, not very sensitive. If you increase the angle of attack, you will get a faster lift buildup, and if you decrease it slightly, you will get a slightly lower lift buildup. And so in that way, it isn't very sensitive to this at all. As for the clap and fling, it's really difficult to say because defining actual shapes in full clap and fling or near clap and fling is actually a lot more difficult than just prescribing the deformation. This was just this is more like a proof. If you could get this shape, this would happen. But to say anything about the sensitivity, it would be rather difficult. So I hope that answers your question. Okay, thanks. Yes, yes, you sure. Okay, yeah.
How useful is this study considering that practically used wings are not rectangular?
Well, so the question is how practical is the study if you consider that real wings are usually not rectangular. Well, the thing is, again, a large part of the study focuses on generation of the leading edge vortex and based on angle of attack near the leading edge. And even if the rest of the wing is a different shape, the generation of a leading edge vortex is always, it's the main lift generating mechanism in insect flapping wing flight. So this will be important no matter how what the shape of the wing, as long as it relies on generating a leading edge vortex for its lift. Got that? Yes, that answer. Okay. Yeah.
Thank you for your presentation. Can you go to slide 15?
15. Yes.
If you look carefully at the dimensional time around 0.5,
Yes.
a little bit negative lift.
Yes.
How is it possible if you have a wing flap at inner fluid at rest, there will be always jet flow afterwards?
So how is it possible that we have negative lift?
Yes.
Well, the thing is, you have to imagine that the motion is entirely prescribed. So the wing actually, initially, the wing, of course, starts to move. Let me think of how that. So if this is your symmetry plane, the wing will move without any deformation like this, But if we add deformation, it will first move like this, and then. So if that's not timed perfectly, then you will get a bit of negative lift due to the deformation not being in sync with the actual motion of the flapping. Is that clear?
Yeah.
Okay. Yes.
There was a question there.
I want to thank you for an interesting talk. I'm not an aerodynamicist, so usually I get lost, but I didn't this time, so thank you for that.
Okay, great.
Then we have this figure here. I wanted to ask about the lift coefficient because we can see that it's not symmetric in downstroke and in upstroke.
Yes.
So I guess it's because you didn't simulate enough wing beats. So I wanted to ask how many wing beats you have to simulate to get something that would be symmetric, so you would have the lots.
No, as a matter of fact, the reason this is not symmetric is because I already used the symmetry plane. So this is a simulation with the symmetry plane at 0.5 to chord length. So in fact, the reason this is not symmetric is because the clap and the fling effect is already present, even for this case. Second interesting part about this is that because I also did single wing simulations, and then sometimes you might have see because I simulated, for example, 10 cycles, and then you can see that because this is hover, so for all the vortices, the wake, it of course builds up, and you can actually see that once in a while suddenly it interacts with the wake, and so it might never become fully periodic simply because it's hover. Does that answer your question?
Yes.
Okay, great, thank you.
One last question. If
No? Oh, yeah.
yeah.
When your vortex separated from the wing,
Yes?
did you find the separation starting from going from the rear of the wing or coming from the leading edge of the wing, or did you notice a difference on it?
So the question is, if when I witnessed vortex separation, did it start at the tip of the wing or the root of the wing?
No.
No, sorry.
At the leading edge
Yes.
or the trailing edge? Did it come from the trailing edge forward or the leading edge back, or some of both?
Okay, so whether it comes from the leading edge down or from the trailing edge up. Well, because you have to imagine, I presume you're talking about leading edge vortex, right? So when the flow will always separate near the leading edge first, and then it will return towards the chord. So it will move like... so it will reattach somewhere along the wing. So separation will always occur when it no longer attaches, so it moves away from the wing. So you get, it's a shape similar to the one in the middle, actually, when you see the separation. However, like I mentioned, I didn't really see clear vortex separation, also because it's, of course, a complete two-dimensional shape, and you also have a tip vortex, so it isn't really clear. And like I mentioned, I didn't see clear vortex separation, so I couldn't really say. Hope this answers your question. Okay, great, thanks.
Okay, then let's thank the speaker again. And we move on to the